hypothesis testing and confidence interval, and specifically it will be on comparing two populations. And in this situation, this is called independent samples or non-paired data as compared to paired data, which is also a situation that arises. So it's important to make that distinction. When comparing two populations, the question concerning hypothesis tests is, are the two means equal of each population? And the alternative comes in one of two forms. Either the alternative is that one mean is greater than the other, or that the two means are not equal. Now, this test of hypotheses has certain assumptions. One of the assumptions is that the samples of each population are representative of the population. So, i.e., a random sample is typically sufficient. A designed experiment is better, but typically is less practical. These samples need to be independent of one another, so one observation cannot affect the other, and each population generally should have a sample size of 30 or more observations. Or they can be normally distributed, which you can verify using a histogram or QQ plot or a box plot. Okay. So our tool for comparing two populations needs to have a statistic. And the statistic that we're going to consider is this one. This is a t-statistic. And under the null hypothesis, we simplify this t-statistic to just be this. The degrees of freedom for this t-statistic are more complicated than in the past. So to calculate the degrees of freedom, we need to calculate this formula and crunch this number. Once we crunch this number, we just take the integer part, or we round down to the nearest integer. Another natural question that arises is what is a confidence interval for these two population means? After all, every time you collect data, you're going to get a slightly different estimate for the sample averages. So what's a reasonable range for this difference in population means? And that's given by this formula. The degrees of freedom is also calculated using that complicated formula just a slide ago. And the assumptions are exactly the same as the hypothesis test. Let's consider this example in which a nutritionist wants to know if a low-carb diet is more effective than a high-protein diet. To test this claim at the 5% level of significance, a random sample of 50 is taken, and 25 individuals are randomly assigned to each group. Assume the data in each treatment group is normally distributed, and the results are displayed in the table on the next slide. So after the data has been collected, they might be nicely summarized for you in this table. And one of the questions that is mentioned in this example is we want to know, are the two diets equally effective at losing weight? Or is the low carb more effective than a high protein diet? Well, the data is where the answer rests. Okay? And so the data, once it's been collected, can be organized into a table that looks something like this, with a sample mean and standard deviation given. The sample sizes are given here. And we want to test this hypothesis at the 5% level of significance. Well, as we alluded to, you need to calculate the t-statistic. And the t-statistic is the observed value minus the hypothesized value, divided by our standard error. Our observed value is just the difference in means. Our hypothesized value is that they're equally effective. That's the hypothesis of the null. Okay? And now we have to compute our standard error. when we compute our standard error, we'll use this formula, and if we plug into the formula, we'll get this 1.16. Now, one of the other difficulties, that we have to do is we have to calculate the degrees of freedom of the t-distribution. So with this data in this slide, we can form the t-statistic, but we also need to calculate the degrees of freedom of the t-distribution. So the degrees of freedom is given by this formula, and we calculate that as 39.29. We only take the integer part, which is just 39. Okay. Now we're ready to test this hypothesis. And I apologize, this should be corrected to 39 here, not 4, but it is on this line right here. So if we're going to calculate this p-value, we're going to calculate the probability a t-distribution with 39 degrees of freedom is bigger than this observed value minus the hypothesized value of 0 and divide by the standard error. Well, this is the information plugged into the formula that we calculated in the previous slides that gives us 1.29. Now, let me show you how we get this 0.102 or 10.2%. Okay. So we'll keep this 1.29, and remember we have 39 degrees of freedom. Okay. So right here I am on the textbook website onlinestatsbook.com, and they have a nice little appendix here for calculators. I'm going to go to the t-distribution, and we have 39 degrees of freedom, and 39 degrees of freedom should go here. Then our value is 1.29 for the t-statistic. Now notice that this is what's called two-tailed, meaning that we have to divide this result in 2. So this 0.2046, we divide it in 2, and that will give us approximately this 10.2, 0.102 or 10.2%. So this is not enough evidence to reject at the 5% level of significance. It does not give us a p-value of 0.05 or less, so we will fail to reject it in this case. Now, this is the p-value method right here. Another method is the critical value method. Our t-statistic is 1.29, and our critical value is 2.13. And in this case, we would also fail to reject, since the t-statistic is, in this case, it should, is less than the critical value of 1.68. Okay. So we get the same conclusion either way. Let me show you how we get this critical value of 1.68. So I have a t-distribution, and we're going to go to t-distribution, inverse t-distribution, and it asks for a a 5% level of significance. Because it was one-tailed, we'll use the 95, and we'll have 39 degrees of freedom. So 1.68 is exactly there, and this should read 1.68 here, and so we also fail to reject. Okay. Now let's work another example. Now suppose a sociologist believes that males have a higher wage than females. To test this hypothesis, a sample of 50 males and 35 females taken is found the average hourly wage is $19.25 per hour, with a standard deviation of $3 per hour for men, and for men it's $24.75 per hour with a standard deviation of 4. Okay, so we wish to test this hypothesis that the mean wage of males is equal to females versus what the researcher is trying to establish, which is that men make more than women. Okay, so in this situation, we calculate the difference in means, that's 5.5. We then calculate our standard error, so we plug in. Now here, the standard error, this is what's referred to as the pooled standard error for both populations. So we have the standard error for men, we have the standard error for women. They're divided by our sample size. We add them, we take the square root. Okay, so that's why this formula is a little bit more complicated, because it's the pooled standard error for the t statistic. Next, we have to calculate the degrees of freedom. We plug in V1 and V2, which are calculated down here. And then we plug them into this formula, and we get 82. So remember, we have to round down to the largest whole integer. So we get 82. And now we're going to calculate the probability the t statistic with 82 degrees of freedom is bigger than the observed value minus the hypothesized value divided by the standard error. And we're going to get 7.23, which gives us a very, very small value. That's 1 times 10 to the minus 10th. And that's certainly less than 5%. Now, we can also ask for a confidence interval on this information. So now that we've done that, we can test the hypothesis by how much more men are paid than women, and this would tell us that we'd use this formula, take the difference in wage plus or minus this t value and divide it by this standard error. Okay, now we have a t distribution with 82 degrees of freedom, and we want 95% confidence. So let me show you how we get this number 1.989. So we go to this inverse t distribution. So inverse t, that's number 7, we're on it. We're asking for 95% confidence, and we have 82 degrees of freedom. So 1.989, and that's the number that goes here. And what this confidence interval says is that we expect that men will make, on the low estimate, will make $3.98 more per hour than women, to as much as $7.01 per hour more. Okay, and I just need to modify this. And I believe that this is the 95%. So this will be our 95% level of confidence. Okay, now here's our final example. Then we'll move on to a case study. So researchers wondered if married or unmarried men have higher testosterone. So you need to state the null hypothesis at the 5% level of significance. So remember, the hypothesis is always one of equality, that married men have as much testosterone as unmarried, and the research only believes that one is different, so this is a two-sided alternative. We're going to test this at the 95% confidence interval to determine what these ranges could be. Now, if the interval contains 0, we fail to reject the null hypothesis, And if it does contain 0, we can reject in favor of one being greater than the other, and the confidence interval will suggest who is bigger than the other. So here's data taken from the study, the influence of marital status on testosterone. And we have our average in our married versus unmarried, and our sample standard deviation is S. For both the married and unmarried group, it's 7.2 for married, 7.5 for unmarried, and here are the corresponding sample sizes. So we need to compute the degrees of freedom. We just use the formula again. We get 324. Okay. So in this analysis, we calculate the 95% confidence interval. We take the differences in averages. We compute the standard error right here, and we get that it's the testosterone is as much as 1.15 on the low side to as much as 2.85 units higher. And we conclude that unmarried men have higher testosterone on average than unmarried men. And this tells us what this range could be. So that was an example from real data in which we calculated by hand. Let's move to our case study. So this case study is similar, and in fact it's the same as your case study if you chose the pay disparity project. Now we have the following data from a job category of a bank that was sued for sex discrimination of 32 male and 61 female employees hired between 1965 and 1975, and we have data on these variables. Now, there's only 2 variables we're going to pay attention to: base salary, or starting salary, and sex. Now, because they're sued for sex discrimination, we're wondering if starting salary differs based on that variable sex. This is what our data looks like. We have more than these observations. This is just a small little snippet of the data. And the question is, do men earn more than women at this bank? And to test this hypothesis at the 1% level of significance. Okay, here's how the analysis would be conducted, and this is the actual output from a computer. It gives us this p-value. Well, that means that we can reject the null hypothesis that the means are equal, that the starting salaries are equal for men versus women. And this is our alternative hypothesis, that the true difference in means is not 0. They don't have the same starting salary. So next we'll look at the 95% confidence interval that's printed. It says that on average, men make on the larger end about $1,100 more than women. On the smaller end, they make $536 more than women. And keep in mind that this data was collected during the 60s and 70s. Okay. So just to recap, from that output, we looked at the p-value to show that, hey, there is a difference. The estimated difference is the difference in averages, so 818. The confidence interval tells us the low and the high that the difference could range from. And it allows us to judge if there is an actual difference in starting salary based on a numeric of the p-value, and also to value the confidence interval. Okay. Now, I'm going to move to our next and final topic, which is comparing two population proportions. So this happens when we have a categorical variable and we're counting counts or instances of that specific trait or characteristic, okay, or category. And to do that, we'll use proportions. That will be our numeric. So this analysis is appropriate when there's a single qualitative response variable with a single characteristic of interest, and the treatment input variable is also qualitative with exactly 2 levels, 2 populations. if we want to compare two populations, we can do a null hypothesis that the two proportions are equal against one of the alternative forms, that either one is bigger than the other or one is not equal to the other. And if we want to test hypothesis, we'll use this z statistic and we'll calculate this numeric. This is our z statistic. Okay. Under the null hypothesis, the P1 and P2 are equal, and we get exactly this. Okay. So this is our simplified t-statistic under the null hypothesis. Okay. Now, we can run this test so long as we meet certain requirements, and even if these requirements aren't met, the test is relatively robust, so typically it's okay, but under an ideal situation, we should have these assumptions or requirements. Okay, so the sample should be independent with 2 levels of treatment. We also need a sufficient number of sample sizes, so both n1 times p1 need to be greater than 10, and n1 times 1 minus p1 should be bigger than 10. And the same holds for the other group, group 2. Okay. Now p hat, this is the total number of individuals in group 1 with the characteristic. P2 is the total number of individuals in group 2 with the characteristic, or I should say proportion here. And p hat, this is the total with the characteristic regardless of group. So T1 plus T2, where T1 is the number with the characteristic in group 1, T2 is the number with the characteristic in group 2. And N1 plus N2 is the total sample size. So we can calculate a confidence interval in this situation, and our confidence interval is given by this formula. Okay, so imagine we have the following scenario in which an experimental drug is being developed and the drug is being tested at 2 different dosages, high and low. The researcher believes that a higher dosage leads to a higher proportion of individuals who experience side effects. State the null and alternative hypothesis and test the claim at the 5% level of significance. So null hypothesis is that the 2 proportions are equal. This would mean that the dosage level doesn't affect the side effects. So it doesn't change the proportion of individuals with side effects. So if you're in the high group or you're in the low group, they have the same proportion of individuals with the side effect. The alternative hypothesis is that the high group has a higher proportion of side effects than the low group. Okay, and that should be a nice little subscript right there. Okay, so that's our alternative hypothesis, which is consistent with what the researcher believes. So we can collect some data, and the data can be organized nicely into a table. The table could look something like this. So under the high dosage, we would know the number of individuals. We could know the sample size. And then we could know the number of individuals that said, yes, I'm experiencing side effects. The same for the low dosage. And notice the numbers are different. We have a different number of a different sample size for the low dosage. And we have a different number of individuals experiencing side effects. Notice that we have more people with experiencing side effects in the low dosage, but the sample size is larger, and hence the sample proportion is smaller for the low dosage. So these proportions are more our metric that we can use to say, hey, yeah, I'm experiencing side effects from this dose. So we need to test the hypothesis. Great. We meet the assumptions. We have 72, which is bigger than 10. We meet the assumptions. We have 77, which is bigger than 10. We're going to need the pooled or average rate of a side effect of 0.112 here. And we calculate this probability, the probability that high is bigger than low for proportions, and it's given by this. According to the statistical theory, I can standardize it, so I divide by the standard deviation here. And that comes from the formula that we had right here. So we use this formula and we calculate it right here. Okay. So we calculate it. It gives us 2.84 once we finally calculate it. This comes from a normal distribution. And we can calculate this using the online calculator, 2.84. I need to select the normal distribution. And this is above 2.84. So 0.0023. And that's pretty much the same number I got here, 0.002. So that's 2%, and that's the p-value. That's less than 5%, so we can reject the null in favor of the alternative. Now, confidence here would also be informative. So we go ahead and we calculate the confidence interval. And we use this nifty little formula that we stated, and then we just plug in the values, and we get 0.18, or 1.8% to 7.5%. So it says the difference in proportion of individuals that experience side effects could be as low as 1.8% or as high as 7.5% more. And one big takeaway we can take from this is that the dosage level does seem to affect the proportion of individuals that experience side effects. This confidence interval helps tell us by how much that could be. So we have a lower estimate and a higher estimate. Okay. Thank you very much.